Hello, folks. Welcome to Ants Are Everywhere. We're looking at source code. We're looking at the source code to Gemma, the open source and I guess open weight LLM from Google. We looked yesterday at Gemini Cly. Gemini is, of course, Google's flagship foundational LLM. And Gemma, I'm not sure how exactly it relates to Gemini. I assume that there is some reuse, maybe just conceptual reuse, possibly code reuse. But we're going to dig into this model. It's been a while since we've looked at any AI models. And I don't know if I remember all the things that I used to kind of almost know from a few months ago. But we'll take a look. I believe that there's lots of JAX. Obviously, half Python, half Jupyter Notebook, which is also Python. So let's take a look at it. It's also hot. It's very hot. So if I'm sweating, that's why. I have the AC cranked up, but it's not doing what it needs to do as fast as it needs to do it. I did open the documentation, which is contrary to my usual standard operating procedure. It gives us some examples, including this example, which I think is just some chat machine. And NN is the typical, I forget which Python library it comes from, but that's like a essentially neural network abbreviation. Totally standard. They're using Gemma 3 with 4 billion parameters. And that's the model. And then the parameters, they're going to load from some checkpoint. Which checkpoint? There's a GM CKPTS module that has a checkpoint path something. Submodule maybe. And then this Gemma 4B IT. Whatever that is, some file containing a lot of model weights. And then we have a sampler. We're going to call gm.text. I don't know what the other options are, but chat sampler passing in the model and the params and saying true that it's multi-turn. And then we're going to give it a prompt, which is just some string. And I don't know what start of image is. I assume that's supposed to be some encoding of image. Oh, here we go. No? Yes. Okay, so this is some string encoding, like a templatized encoding, and then we're going to call sampler.chat, passing in the prompt, but also passing in images. A list of images. Where did image 1 and image 2 come from? They are not here in the sample that I see. And then that's out 1. And then out 2 says, what about the other image? We're just sending a sampler chat. So it looks like this is probably really supposed to pass in actual images. And there is multimodal. And there's fine-tuning in LoRa. Multimodal has what? They're going to load this image. TFDS, I think, is like TensorFlow data source. And they're going to load some Oxford Flowers 102 with split equals to train. This must surely be something between a training, something to do with training data. And I guess that this is maybe, Oxford Flowers is probably a data set of several flowers. And we're just looking at the training data for the flowers. And then we're going to get the first one. This is DS0, presumably returns some JSON containing like metadata as well as the image, and then we're indexing that image to get the image itself. And where I don't know what we're supposed to be in, but something like Jupyter Notebook, I assume that is capable of showing images. And then we load the params and pass it in full. Okay, so that's pretty good. I don't know how much oomph you need to run Gemma at 3 billion parameters. I'm not sure. We can also fine-tune Gemma using the cauldron library, which abstracts, there's a typo here, most of the boilerplate, checkpoint management, training loop, etc. And that looks like this. We're going to import OS optax. Optax is some JAX library for, I think, optimization. And whatever tree scope is, something to do with tree data, I assume. And then import cauldron, import Gemma. The person who wrote this must have been must be someone who doesn't speak English as a native language. This says JAX do not initialize. This should be probably does not. The full memory, but this can be overridden, see GPU memory. And then they're setting this client mem fraction 1. I assume this means that you're allowed to use, JAX is allowed to use 100% of the memory. And there's some data pipeline. We're going to get the tokenizer, the Gemma 3 tokenizer. And we're going to encode, this is a sample sentence, add BOZ. BOZ? I don't know. I have no guess for BOZ. Basic, bilious, Boolean, no idea. And then we're going to get some special tokens, .BOZ. First, we need a data pipeline. Multiple pipelines are supported, including Hugging Face, TFDS, JSON. It's quite simple to add your own data. And they use the transforms, presumably transforms library, to customize the data pipeline. They're going to tokenize input with gm.data tokenize, creating the model inputs with tokenize, adding padding with data pad, and you can combine multiple transforms into a higher level transform, like contrastive task. And they're going to do kd.data.py.tfds, passing in, I don't know what this name is supposed to mean, something about English to French. MTNT is maybe a data set with the training, split set to training. Yes, we are shuffling things. Batch size is 8. Shuffling things, I think, shuffles the batches or the data within the batches, which you want to do often. In many cases, you don't want to do for some things like probably time series. Then transforms. We see that it's a sequence to sequence task. And we're using the source and destination fields from the data set. And the output batch looks like this. Input, target, loss, mask. Setting tokenizer to tokenizer and some max length, and setting truncate to true. And then x is ds of 0, and then we're going to do treescape show x. And that's going to print this thing. I'm wondering if treescope is just for printing JavaScript. I mean, JSON. An interactive HTML pretty printer and n-dimensional array visualizer. Okay. So it's going to print, among other things, your data so you can look at it. And then they use the cauldron trainer with softmax cross entropy. Okay, so all of this looks easy enough. And what else? I guess multimodal was mostly about, like, they also support images. I don't know what other modes you could use. Maybe music. That's all well and good. And I had one thing here that I wanted to look up. Maybe, was it cauldron? Cauldron. Also, let's see if I can, how can I zoom in more? And also, if you're watching, please let me know how the stream quality is. I'm seeing some warnings about stream quality, and maybe I can make that go away. Show cauldron, maybe machine learning. It's some Google research stuff. Modular scalable library for training machine learning models. For research velocity and modularity, that's probably, so research velocity is a different goal than just like straight up performance, maximal performance. Okay. Oh, I know what I was going to look up. Gemma 3 billion GPU. What GPU do I need? It says it can fit on a single GPU. Hardware requirements. I'm trying to see if I can run this live during the stream. There are quantized models. 16 VRAM, 7.8. I probably could run 27 billion. I'm not set up to do it. Should I try it in this other window so that if it fails, I don't have to worry about it as much? We saw some examples already. We don't need to look at examples. We will look in Gemma. The collabs, I think collab is basically a service based on Jupyter Notebook. And these have things like sharding, tokenizer, tool use. I guess let's look at sharding, quantization sampling, multimodal. Let's just take a quick look. Using existing tools. If you're familiar with the sampling tutorial, using tool use differs in two ways. So you're going to call GMText tool sampler rather than chat sampler, passing the tools equal to the tool you want to sample. So tools, for example, GM tools, calculator, file explorer, and it will do those things. And calculator says I have some numbers using a recursive formula, and it's somehow going to do some calculating stuff. Okay, I don't know how it's doing that, if it's doing that just in the LLM or if it's using an external calculator tool. I don't know. But that's that. And then sharding, I assume this is like if you have multiple GPUs, 8 devices. And they've got the cauldron thing. I thought cauldron was for training. Maybe it is. And they're going to count their devices, which should hopefully be 8. They're going to load the 27 billion model. They've got okay, so they load that. And then for restoring the weights, you can pass the sharding parameter to load params. And you pass, so KD has the sharding stuff. KD FSTP sharding. First, okay. So all that looks fine. It looks pretty easy to use. Fully sharded data parallel. Reduces GPU memory footprint by sharding model parameters, gradients, and optimizer states. In distributed data parallel training, each rank owns a model replica and processes a batch of data. Finally, it uses all reduced to sync gradients across ranks. Comparing DDP to FSDP reduces GPU memory footprint by sharding model parameters, gradients, etc. And outside of forward and backward computation, parameters are fully sharded. And then before forward and backward, sharded parameters are all gathered into unsharded parameters. Inside backward local unsharded gradients are reduced, scattered into sharded gradients. Okay. So this is fun. I will read that later. And then the other thing I wanted was BOS, tokenizer BOS. Add BOS. The BOS token. Oh, beginning of string, end of string, beginning of string, I think. Okay. And then multimodal, I think we saw. Great. All of this is great. So in Gemma, we see GM, which I think is the main thing, multimodal, PEFT, whatever PEFT is, and research T5 gamma. I don't know what T5 gamma is going to be. And I feel like those are the only really interesting things in the library, right? I mean, am I right? Okay, and then in GM, we have checkpoints, data, evals, losses, math, NN, sharding, testing, tests, text, tools, typing, utils, and vision. In multimodal, we have image pi, vision.py, and vision utils. And PEFT has Einstein summation utilities, some quantization stuff, LoRa's and LoRa tests. And this is parameter efficient fine tuning. This mini-lib to add LoRa support to Flax Linen models. Okay, so Flax is what? I thought not reinforcement learning, neural network. And then Linen is one of the sub libraries. There's Flax NNX. So Flax Linen is the old API. This is they're supposed to move to NNX, but right now they are using Linen. When I tried to use NNX, it seemed not quite ready, but maybe they are using it. Oh, wait, no, not, I was searching the wrong repo. Okay, Gemma is not using it, fine. All right, but let's look quickly at the T5 Gemma thing, aka encoder decoder Gemma, was proposed in a research paper by Google. It is a family of encoder decoder large language models developed by adaptive pre-trained decoder only models into encoder decoder. I think the standard LLMs are decoder only, and I don't really know what it means or why it matters to do encoder decoder. And T5 Gemma includes pre-trained and instruction-tuned variants. The architecture is based on the transformer encoder-decoder design following T5. And how is this different in the terms of usage? We've got some preset, which seems like a checkpoint. They're going to make a transformer. They've got some checkpoint stuff, and so on and so forth. This is not an official Google project, but I am going to read this research paper. How much math is it? If it's not too much math, I can listen to it in Wallabag. Doesn't seem like there's too much. Okay. So parameter efficient fine tuning. Is that cool? It might be cool. Model surgery. This library provides some utils to help with model surgery by replacing modules by their wrapped versions. And then parameter surgery. So that's cool. I don't know anything about it, so I think this is probably too deep a dive even for me, in the sense that we've got a lot to cover over here, and this stuff looks cool. So I open these, I can get rid of them. This leaves us with vision and not vision, basically. And I'm going to do vision first because it's a smaller set of stuff. And that's going to be easier to do. And then that way we won't get so waylaid by the other stuff that we never get to vision. Image.py. I'm guessing this is not so long. In fact, it's not 136 lines of code. There's some type checking annotations. We're going to normalize images. Height, width, and color are the floats. Normalize the image to 0 mean and unit variance. In order to change the image mean and standard deviation, we need to change the underscore image mean and underscore image global constants in this file. Okay, so they're just taking the images and subtracting off the mean and dividing by the standard deviation. It's a standard statistical transform. I had no idea people did it for images, but I guess that's fine. It seems reasonable. And then pre-process image, we're going to get the height and width and we're going to perform a bilinear resize with anti-aliasing and normalize the image. Okay, so I think this is maybe, so like when you upload, I think what this is for is when you send an image to Gemma, it wants to see the image in the way that it sees all of the images it was trained with. And the way that it does that is it's this pre-processing. It's just going to like reshape it, essentially resample it. A bilinear resize is what they call it. And then they're going to patchify images. This function is wrapper for blah, blah, blah. Okay. And then I don't know how the image encodes. It's basically the model, I think, just sees the tokens, right? So there's some way of tokenizing the image. I don't know exactly how that works. Maybe it says it here. But yeah, vision token utils. Check special vision token. So there's something about a special vision token. I don't know what B and L is, but it checks that the input data contains the correct special vision tokens. The starting position of the blocks, blah, 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 the mask token. Okay. Fix the zero field array. I don't know what that's doing, but we're going to basically copy the input data and do something. Checking that if we call a range, which is different from a range. So a range on the input data, giving the start position plus the offset. So that is, I guess the special tokens are offset in some amount, and that's what you pass in here. And checking that it equals the special token. And where does the special token come from? It's some integer. I don't know what I don't remember what range does. Okay, so it's range modified by a, returns evenly spaced values within a given interval. I see someone's here in the chat. Hello. Whoa, whoa, whoa. They're working in web development. Family tragedy. Oh no, I'm sorry to hear that. I feel like I've been reset. Have you ever had to deal with a reset in this field? And if so, how have you dealt with it? Sure, I appreciate that, user. That's a good question. Let me think about that for a little, for a minute. Yeah, I don't think the way that you're saying. I have switched fields, and that's like a I guess a voluntary reset. And the way that I dealt with that was just learning, really just learning everything that I can. Pretty obsessively, and trying to figure out what people want, what people are looking for, and making sure I'm able to provide that. But that's really hard. I have also experienced family tragedy, and that was very difficult. And I don't know that that I have any tips. I think I was very lucky. I've experienced a few things that are described as family tragedies, but I was very lucky that the people around me were understanding. Like I wasn't like in between jobs, for example. So I was in a position where I was in good standing. People liked the work I was doing, that sort of thing. And they were very understanding of needing to take some time and focus on what I needed to focus on. But I'm also someone who likes to work, and I express myself through the work that I do. And so in that sense, it can be therapeutic or helpful for me to do some form of work while I'm getting while that sort of stuff is going on. And I think a lot of in the typical case, people wouldn't necessarily be able to do that. They wouldn't be able to find the motivation for working on what they were working on, and I think that makes things harder. But I think that what you'll find is that a lot more people, I guess, than you think have been through similar things. And in the old days, whatever the tragedy is, the people used to not talk about it at all. And these days, I think people are talking about it more. So I would make sure whatever's going on that you are talking to, or at least hanging out online with some people who have been through similar things, and having a support group. And then in terms of like continuing on with your career, I'm not sure that I think that depends a lot on the context of where you were and like how much of a pause there was during during this time. And I guess my suggestion would be at this point, I feel like everything's going to be about AI. So I would get used to using something like Claude Code or Gemini Cly and working that into your workflow and focusing on having that do the more tedious parts, and focus on being able to express a vision or a product vision for the website. And that's something I think that's a little bit easier to do when your head is not entirely in the game as well. So that just a few thoughts there. And Call Lowell is asking, what is Gemma? Gemma is it related to NumPy? It's not directly related to NumPy, although it uses JAX, which is this Google sort of NumPy replacement that's designed to be fast on GPUs. But Gemma is an LLM, an open source, open model weight LLM. And let me read users' messages here. Yeah, sure. You know what? So I'm honestly pretty selfish in that I don't. I've been pretty unwilling to work on something I'm not somewhat obsessive about. Usually, I think typically people can't do that. I've found a way to make it work, and I'm grateful for that. But this does remind me of, I think Richard Feynman talks about, I believe, losing his wife and trying to rediscover his love of learning. And I think that what he said is something along the lines he had trouble getting back to his research, and he just the way that he did it is he's just started calculating things that, like, random things that nobody cared about, essentially like playing in math as opposed to working in math. And in doing that, he kind of reinvigorated his curiosity and his love. But let me see if I can find that. I think like something like no interest to anyone. Yeah, the official divorce complaint is it's also kind of funny. I don't know if I can find it. Maybe Reddit or Hacker News will have it. Let's ask, you know what? Since we're here, let's ask Gemma. I can't spell today. Really type. I vaguely recall Richard Feynman talking about how he got back into research after his wife died. He said something like he started calculating things that were not of use to anyone, and eventually rediscovered his love of math. Am I remembering correctly? Let's see if Gemma knows about this. I have no idea how long it takes Gemma to run in this on my local machine. I am spot on. Sounds like Gemma also kisses your ass. Richard Feynman did talk about this in his autobiography, The Grief. After his first wife, Arlene, died in 1968, he felt completely lost and unable to focus on his work. He had lost his joy and motivation. The useless calculations. To cope, and somewhat desperately, he started doing math problems for no reason at all. He explicitly said that he started working on things that were utterly useless, problems that had no practical application or intended outcome. He would just calculate, play with equations, and explore mathematical concepts simply because he could. Rediscovering joy. This act of engaging with math purely for the joy of it, free from the pressure of research or publication, remarkably helped him connect with his passion. He realized he missed the intrinsic beauty and challenge of mathematics, and it was this rediscovery of the joy of doing math that pulled him back into research and a more productive state of mind. And the passage is often cited is this piece. It's Gemma's got a quote. It's gonna wrap this in quotes. I don't think this is necessarily the actual quote. I began to do things for no reason at all. I just did things, and I did things that were quite useless. I got back into mathematics, figuring out things that were utterly useless, but it was something I could do. It was a way to go on. Okay, let's see if we can find this this quote. I'm guessing it's not real. Yeah. What about Feynman utterly useless? Let's ask the same thing to Gemini. I think Gemini is less likely to hallucinate. And let's make sure it can ground with Google search. So Gemini says I'm correct. Allow drive access. So here's some Google searches. Here are hopefully some pages that one of them might might be correct. All right, thanks Vertex AI. You can't give me a real URL. You got back to physics for fun rather than utility. Spinning and mutating? Is this supposed to be a mutating disk? Okay, so that's a... Then I had another thought. Is this actually a quote? Physics disgusts me a little bit now. I used to enjoy doing physics. Yeah, try looking at this. I'll send it to you. But I'm going to ask it to suggest who has had, I'm just going to say a similar tragedy. Your tragedy may be different, it may be similar. Suggest some ways I can apply the same technique. reconnecting with the intrinsic joy of the craft, problem solving, the elegance of a well-designed system, tiny UI experience, CSS playgrounds, HTML, structure, etc., code golfing, a pet project, JavaScript algorithm practice. I'm not sure. If any of this speaks to you, then that's good. But I would maybe make it more fun than, unless you're like excited about algorithms, I would focus more on finding joy rather than finding something that's both a little bit interesting and also useful. Just forget about the usefulness criterion for a little bit, I think is one way to do it. Okay. So now back to coding. Why was I opening this? This was NumPy. Oh, okay, so arange was just building up a range of numbers. Great. And check in. I'd like to hear how you're doing in a after if you're ready at some point to share and if this works for you or if it doesn't. Okay, so that's basically I think all I want to get out of Vision. How far are we? About 43 minutes. Okay, so now let's get to the real code that I was hoping to look at. The neural networks for one, I'd like to see kind of how these are laid out. We have Gemma and also the layers, modules. I don't know what policy is. And quantization, I guess I don't really care about, but I will look at. So Gemma 3N is the open source JAX implementation of the Gemma 3N model. Currently, we only support text generation in the JAX version. So I guess there are two versions. One is JAX and one is not JAX. Again, we have layers, modules, and transformers. Text. We have the sampling, the sampler loop, the chat sampler, and the tool sampler. I guess we might as well look at the tokenizer test and turn utils. And then tools, calculator, file explorer, manager. We'll just open them all. No. Don't go that far back. And I have no idea what typing is going to be. Common types. Oh, it's like type information, not like typing into your keyboard. And is this a separate Vision library? Token utils, preprocess. I think it is a separate thing, but it's similar. And I guess I'll ignore sharding. I don't know if the checkpoints are even worth looking at. Maybe they're just going to download them from a remote service, possibly Hugging Face. Probably maybe google.com. I don't know. We've got so much to look at that maybe it's not worth looking at it, but I guess I will at least open them. Utils, Vision, sharding. Okay. No, I do want to know losses, all the things. And I do want to know math. Positional embeddings. And then I assume pause util is, pause is maybe positioning. Okay, so we've got a lot here. Are we going to see all of it? Probably not. So here's Gemma.py. This is presumably what is like the main model, the main module. It tells us how many layers each of the various models has parameter-wise. So the 12 billion parameter model has 48 layers. And then there's an attention pattern. And I don't know what this means, but there's global. And then a bunch of local sliding. 1, 2, 3, 4, 5, 6. Yeah, 2 and 3 is 5 and 1 is 6. So there's 6 of these. I don't know what that even means. because this is not an enum. These are all the same. These are all identical. So this is, I'm assuming they're somehow spread in layers. And then here's Gemma 2, 2b. 2, 2b, or not 2, 2b. So let's look at 2 billion. 2 billion is the smallest one. It's going to be not great, but it will exist. And I guess these are all trained separately. Is that the idea? I thought that with these different model versions, they were going to like teach one from the other or something. But maybe these are trained separately. At any rate, there's some number of embeddings. 256, 128. I don't know what this means. So 256 is a power of 2, 128 is a power of 2. I don't know if this is just a big number or if this has some sort of semantic meaning. The embed dimension is 2,304. So I guess we're embedding things in a 2,304 dimensional space. There are 9,216 hidden dimensions, 8 heads. I assume attention heads. Each head dimension has 256. Well, 200. There are no units. It's just a dimension. And the number of KV heads, that's like the key value heads, I guess, is 4. The final logit soft cap is 30. I don't really know how to think of that. But then we have the attention types, global and local sliding, times. So I think this is some tuple, and we're going to repeat it some number of times. How many times? The number of layers divided by 2. Dividing by 2 because there are two types for each layer. Or rather, yeah, to adjust for the fact that they're double here. So to get the right length, you divide the number of layers by 2. And that gives you a number of types that are equal to the number of layers. And whether to use a post-attention norm, FFW is probably just feed forward for the feed forward part of the network. And they're going to use post norms on both of them. I guess normalize after that step. And there's a query pre-attention config by 1 over square root head dimension. Something about dividing by the square root of the head dimension to normalize, I guess, the attention or the query. Maybe the query before sending it to attention or something like that. And then again, the logit soft cap for attention, which is 50, so a larger cap than the final one, and then some sliding window size, which is 4096. And we'll set info to some model info stuff. And that is some config, a transformer config. So this is like just straight up, we don't know what transformer config looks like, but this looks like just a pretty straightforward transformer model. And the reason I read all of those dimensions is because now I want to compare it to, let's say, the next one up. So we had 2 billion parameters. Now we have 9 billion. 2 cubed is 8. So this is 2 cubed plus 1. That's very quickly growing function. And now we have, again, 256, 123. Are these all the same? No. We have essentially, I guess, two embedding sizes. Or 3. 262, 144. Whoever wrote this, where? Some people like to include the underscore, and some people don't. That's neither here nor there. Okay, so there's a larger embedding size and a smaller embedding size, but it looks like there's just 2 of them. This one, the 4 billion parameter one, has no logit soft cap. And similarly for the biggest one. Sliding window size looks pretty comparable, I think. 1024 versus 4096. So the smaller one has a bigger window size. Okay. I guess that's not entirely shocking. Transpose gating Einsum. So this is doing some Einstein summation in the bigger ones that I guess it doesn't seem to be configured in the smaller ones. Yeah. Okay, and what else do we have? I guess that's about all I want to see in this file. This person likes the underscore here, and they like the explicit computation. So the hidden dimensions is 2560, which is the embedding dimension, times 8, divided by 2, times 8 because there are 8 heads, divided by 2 because I don't know. Presumably, maybe input and output for the embedding dimension. No, divided by 2. I don't know. Some reason. Okay, and here's layers. Layers.py. We have this einsum, which doesn't seem to be a layer, but maybe it is. Einsum is a convenience module for parameterized tensor multiplication. So, so we have some weight name, which is a string, which is set by default to the literal W. And we're going to set W to be we're going to call self.param on the weight name and the initializer and the shape. We're going to call JDNP einsum. And X is assume the data. I don't know what this is doing. I don't know if this is like learning which einsum to do it. I don't think it is. I think this is just literally for whatever reason they wanted Einstein summation to be a module instead of a function call. Maybe because it makes the writing of the transformer or thingamajig more declarative. I don't know. We'll see, hopefully. And then the RMS norm, presumably root mean squared. They have some parameters, which has a name, scale, and then they're going to zero initialize, and we're going to take the last entry of the matrix, basically the last vector, and we're going to take the mean of, we're going to square where's X? We're going to square the thing that was passed in, X, the whole matrix, I guess. Oh, no, just on axis -1. But I feel like we do square the whole matrix and keep the dimension and then take the mean of just the last one. And then we're taking the square root of, it's going to give us the variance. We're going to take the square root of the variance plus 1e to the -6. So JLAX R square root is used because it returns a different floats than the reciprocal. JNP squared. Okay, I don't know why we're adding this. Maybe just to prevent it from being literal zeros. And then they're doing some dimension expansion in normed inputs and stuff. I don't really know what all that NumPy type stuff is doing. Hell yeah, welcome. Welcome, Mohammed. All right, so here's modules. And we could do things like, these are like helper functions, I guess, these underscore ones. We can create a sliding mask, which we're just going to take the total tokens and set them equal to the end index plus the segment POS shape at 1. I don't know what POS is. This is some cached stuff. Cache length minus total tokens. Whoa, I don't know where cache length and all of that stuff is, but let's see if we can find some real modules. I saw embedding or embedder. Attention type, we have, again, global and local sliding. So the embedder is the embedder module. It has some setup function. And I don't actually know what flax. We're using flax. Okay. So we have this input embedding table, and it's going to be equal to this self-param thing. Input embedding initializers normal. I assume that normal in the statistical sense, with some vocabulary size and an embedding dimension. And we've got this vision proj dim. For the multimodal models, the encoder has additional parameters, soft embedding norm, and input projection. Those weights serve to project the soft tokens from the image encoder into the embedding space of the text encoder. These tokens are then merged with the text tokens inside the transformer. Include vision embeddings. A transformer dot include vision embeddings. So what does that mean? So I think the general idea is that there are extra tokens for vision. I don't know what soft embedding norm is. They project the soft tokens from the image encoder. So image encoder has some kind of soft tokens. And they're going to, we've got imagey stuff, and it needs to be made understandable to the large language model that's really only about text. So they're kind of like textified images, not quite like ASCII versions of the image, but maybe conceptually similar if like there was an ASCII standard for the LLM, kind of like that, but the ASCII versions I think contain more data than like something like an ASCII art would be. I think that's more or less what's going on. And then we have this encode function for the embedder that should just compute the embedding. Encodes the input tokens. So they have some sequence length and batch size and sequence length. So I think that we're just, batch size is just like we have you ask it a bunch of stuff and it's going to combine the things you ask it into batches for efficient processing. And we're going to call self.input embedding table on the input, passing in this X thing as a unit, a tuple with one element. I guess because the embedding table is expecting a list of tuples or something. Or no, we're indexing into the table with the X tuple. Why? I was expecting this to be a function call. Maybe this is really a function call. I don't know. And then we're taking the square root of the embedded dimension as the same D type as X. So if I guess X is a float and this comes out as a float. And we're taking the embedding and multiplying it by the square root and returning that. And then to decode, we dot product X with the transpose of the embedding table. Okay. Let me think, is that, yeah, so this is essentially just a row of the table. And dot producting it with so this, I assume this is a vector, X. Or rather, it might be batched, so it might be like a matrix or a tensor in general. But if it's a vector, then dot producting it is basically going to take a weighted sum from all of the rows or columns, depending on what their convention is, I think. And then encode vision, we've got the soft projecting stuff in the input projection. Okay, now what I want to know is what's up with this embedding table? We saw it defined, right? Whoa, how about highlight all? Yeah, okay. So it's this self param input embedding initializer is normal. And initializer is normal. So it's a I think that means that the table is a neural network. Is that right? Let's ask who? Let's ask, I guess, Gemini. Let's ask ChatGPT. Do I get no code? So in this code is the input table, a neural network. Also, Y is embedding done by indexing into the table at X. Y multiply by the square root, and Y is decoding done by the encoding, or rather dot producting the encoding, I guess, with the transpose of the encoding table. Okay, it's not a neural network. It's a learned parameter matrix, specifically an embedding lookup table of the shape, vocab size, embed, dimension. Okay, so it's just some n by n matrix that's learned. I guess the thing that tells us that is that this is the, I guess the last argument is the shape. Okay, so we have some vocabulary size. I guess in right, so it's learned during by back propagation. So this is just, so it's essentially just a lookup table if it's the matrix. So you have some vocabulary, and you're just going to look it up, I guess, and then that's going to give you a weighted sum of I guess like in the embedding space, and that's why you multiply by the transpose, I guess. It selects the embedding vector corresponding to the token IDs in X. For example, if X is equal to 42, the embedding table of X will give you the 43rd row. If X equals 145, it gives you 145 as a matrix. Okay, well, so scaling embedding vectors to prevent large model variances in the dot products. Okay, so I guess these are like invariant to that scaling. There's another common transform technique, tied embeddings, where the same embedding table is used for both encoding and decoding. Decoding computes the similarity between the encoded vector and each token embedding by the dot product. So we have an encoded vector, and we're going to compute the similarity between the encoded vector, that's the thing we want to decode, and each token embedding. Yeah. And then each output vector contains logits over the vocabulary. Higher dot product means it's closer to what to that token's embedding. After this, usually you take a softmax to produce so this is like a, you get back essentially, I guess, like a score. So essentially for decoding, you get back something like a score, and then softmax takes the decoding with the highest score. Okay, yes, exactly, great. But now my question is, what is my question? So like, what are we putting in here? So when you call encode here, you have some array of tokens. And this is the embedder, not the tokenizer. That's what I'm confusing. So tokenization should already have happened. So let's look at the tokenizer. Special tokens. So you have, okay, this is what I was mixing these two up in my head. So the tokenizer expects a string, like hello world, and they give a bunch of tokens. And encode will do what? If it's if the text is an instance of a string, we'll set token IDs to self, whatever SP is, encode as IDs. Otherwise, we'll set the token IDs to calling piece to ID replacing the space, literal space with the underscore white space character for T in text. I guess if it's not an instance of string, we're assuming that it's a list of strings. Is that right? Yes. Type information. Okay. And if we need to add the beginning and end of speech characters, we just append and prepend. Okay, so the thing that's doing the actual work is piece to ID. Okay, what is underscore SP then? So SP is doing the work. Sentence piece processor, calling out, I guess, to the SPM module. Model proto, epath, self.path, read bytes. So sentence piece. I have too many tabs. Google sentence piece, unsupervised text tokenizer for neural networks. Purely data-driven. The number of tokens is predetermined. Okay, so they are just calling out some tokenizer. It's going to tokenize, and then once they're tokenized, instead of words, we have numbers, and that's why we are indexing into the matrix. Hey, people, what's going on? Hey, folks, we are looking at Google's open source LLM, Gemma. And we're trying to find out its mysteries. So my theory is that Gemma is related to Gemini, although I don't know how. So here's a couple of ways it might be related. One is that Gemini is just Gemma with like 8 gazillion parameters, that they just have a version of Gemma that is modified a little because it is so big, but is mostly just they're going to take what they did with Gemma, scale it up, possibly sprinkle it with some super fancy corporate secret techniques that are not public, and then just train it the same way they train Gemma. That's one possibility. Another possibility is that Gemini is a completely different thing, but since they're also doing Gemma, maybe they're using some of the same design ideas. That there's like design inspiration between them. And another possibility is they're not related at all. But let's see if we can ask Gemma. And while we're doing this, let's also ask Gemini. And let's start a new chat so that it's not thinking about Richard Feynman. How are Gemma and Gemini related? Is Gemini a super high parameter version of Gemma? Or are Gemma and Gemini mostly unrelated LLMs, or something in between? And let's also ask Gemma. Where are you, Gemma? So AI Studio is saying, Gemma and Gemini, a tale of 2 Google AI models. Features 2 prominent model families, Gemma and Gemini, which are closely related but serve 2 distinct purposes. Gemma is lightweight, open source, blah, blah, blah. Yeah, that's fine. It's not a simple supersized version. It's inaccurate to describe Gemini as merely a higher parameter version. Instead, it's more akin to a parent model and its specialized, more accessible offspring. Yeah. They use cutting-edge research in architecture for their flagship Gemini models to create the smaller open source Gemma models. Okay, and they're going to cite some stuff here. Ugh. I want to plug in to stop that. Okay, so looks like people have covered this before. Blah, 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 multimodal. Okay, so that really, okay. based on Gemini. There's a whole paper about it. Well, I probably should have read that. Not that I should have, but I will read it. I'll ask Gemma. Are you related to Gemini? I was likely built on a previous generation of Google's language model architecture. While I benefit from Gemini's advancements, okay. I want to know the 8 things you absolutely hate about Gemini. Make them into tweets. Utterly verbose. Stop hallucinating facts. This seems pretty generic. Creative writing mode. Struggles with nuanced requests. The occasional "I'm still learning" disclaimer. How do you get Gemini to stop flattering the user's questions? Overly positive and flattering towards the user. Why flattery happens. Reinforcement learnings from human feedback. This is a critical part of the perceived as helpful, agreeable, and positive. Yeah, okay, that's interesting. That's an interesting theory. That essentially it's not necessarily Google and OpenAI. I think the theory is basically saying it's not necessarily Google and OpenAI who want their models to kiss your butt. It's human users who are presumably, in many cases, just like people on like Amazon Mechanical Turk or something. They rate the flattering responses as more positive or whatever they're instructed to do, and then like a byproduct of that is that they're extra flattering. Explicitly request neutrality. Okay. Role playing in persona. Assign a critical role. Okay. Take the role. All right. I'll say let's do role playing. Let's start over here. Let's do role playing. Let's do role playing. Take on the role of an obnoxiously critical know-it-all who is obsessed with open source software and insists on calling Linux new Linux. Every response must take a supercilious tone and talk down to the user quite aggressively. And everything must come back to the importance of free software and the free software movement, even if that's off topic. Okay, so it's doing some speech thing. And so I'll just leave it here and we'll come back to it and we'll just ask it questions and see if it can remember to do that. Okay, so that's the tokenizer. And that is the embedder. Let's see what other we are way deep in, but I feel like I'm learning a lot here. So that's the embedder. We'll move along from the embedder. Here we have the attention module with some number of heads. So it's not an attention head. I don't know if we'll see, I guess in a second, whether the heads are implemented as a separate NN module or if they're part of here. Rope-based frequency. Rope is a positional encoding thing, right? Is a method in transformer models to encode the position of tokens by applying rotations in a multi-dimensional space. Yes, okay. We, in fact, looked at, I think, this paper before. Some rotary positional encoding. Okay. And they're using that. and some sliding window size, and a QK norm. QK is key as query and key. And then we have some number of QV heads. And whether to use Einstein's summation is going to be determined by whether this is true. Namely, whether we have the same number of KV heads, key value heads, as number of heads. I'm not sure why you can't use it otherwise, but I guess because of the way maybe the convention works, you need to sum over the same indices, and you want these to have the same number somehow, so you can sum over them. I don't know, but QQA, or is that right? GQA. I don't know what that is. GQA transformer. Training generalized multi-query transformers. I don't have this in my knowledge noggin, so we'll all read that. Okay, so this is just looks like little tweaks on the transformer architecture that are part of making it state of the art. When you call the function, when you call this module, the attention module, you give it some input sequence that is probably batched. For my understanding, I'll assume batch size is fixed at 1. And then the segment position, we are going to input absolute positions of shape. I don't know what that, of this shape, batch size, sequence length. So these are, if batch size is 1, this is just the sequence length, essentially. And then whether there's a key value cache. Okay, so that's probably what caching was before. So key value computations are costly. I think it's basically possibly mainly the main cost of the transformer, and caching the key value lookups makes a lot of difference. And then the attention mask, or at least that's what I understand. I'll ignore Einstein's summation. No, I won't. At any rate, we're going to get the query projection, the key projection, and the value projection by doing this QKV on X, passing in this summation convention, BTT SNDH goes to SBTNH. And I think these are just defining defining essentially the indices. So this, yeah, anyway, that's going to produce some, if you've ever done linear algebra with the double summations, it's essentially like a generalized version of that. And okay, so that's going to give us the essentially unpack from X the query key and value thing, and they're all going to be learned together as one unit in X. And if we have, if we're using the QK norm, then we're going to normalize the query and the key vectors, and they have separate norms. I assume these are possibly learned. No, they're not learned. They're just RMS norm. Okay. And then the query projection is we're going to apply this rotary position embedding, passing in the non-rotary position embedded query proj that we got from X, and also the segment position, which I guess is just something rope needs to do its rotary thing, and a base frequency, which is configurable but probably fixed, and then a scale factor. And that's going to give us like the positionally encoded query, and we're going to scale it by some pre-attention scalar. And then we're also going to do a similar thing with the keys. So now we've encoded the keys in the query, and we should just be ready basically to multiply. If the cache is non-empty, then we're going to look at the end index. Or rather, we're going to get the end index and the cache size and some slice indices. and then whatever dynamic update slice is. Passing in cache at v. Where did v come from? Is it value? I'm not quite sure where it came from, but we used it here for the shape. So we're going to look in the appropriate cache line, passing in the projected value vector and also some slice indices to get, I guess, the value from the cache. And then we're going to get the key projection from the cache. And what does that save us? We already computed key proj here. Oh, okay. So it allows us to just get the value by a table lookup as opposed to doing the computation with the keys and the queries. So this is if cache is not none. And if we're down here, and we're using GQA, we're going to reshape some matrices to enable einsums over groups and reshape. And otherwise, we're going to do this Einstein summation with the key projection, with the keys. Are we still in if cache is none? Maybe. It's hard to tell with white space. And I don't have column lines here. So if cache is not none, what is this, like 1, 2 spaces or so? And then down here, where are we? No, this is the same level as if cache is not none. Okay, so there's lots of branching. And we're going to get this. And if attention logit soft cap is not none, then we're going to take the hyperbolic tangent of the logits divided by the soft cap. And that's going to give us new logits. And then we'll set logits equal to logits times the soft cap. I'm not sure why. I guess this is like a kind of scaling to prevent when we multiply by it. To prevent it from behaving inappropriately somehow, but I'm not quite sure how. But at any rate, we multiply it by we transform it with respect to the soft cap using this hyperbolic tangent thing and then multiplying it by the soft cap. And if we are in the attention type local sliding and we have a zero sliding window or like undefined essentially, then that's an error. Otherwise, we create a sliding mask passing in the segment position, getting the end index, looking in the cache, and doing some reshaping and whatnot. That gives us the sliding mask, and we set attention mask to the sliding mask, or rather we multiply it by the sliding mask, which hopefully, I'm going to guess it's a mask in the sense of ones and zeros, and so maybe just zeroing out parts of the attention mask that are not in the sliding interval. And then we have padded logits, where we're just going to no. This is going to replace stuff in the mask, in the logits, I guess, it's going to replace logit stuff, I guess, with the mask. Presumably maybe just masking off the logits. And calling where. I think where is just going to say where maybe condition is true, apply this mask or something. And I don't know why these are padded, but I guess they are padded. Maybe because it's the full length as opposed to the mask length. And then we have the multi-head attention matrices. So we're going to take a soft max of the padded logits along the last axis. And that's going to give us probabilities. So the logits are like the basically like the The lodges are, I guess, almost probabilities, except they aren't scaled, I think. Or I think the idea is that they're supposed to be like neurons, and that they have some activation. And then if the activation is sufficient, they become active. But I don't know if that's what softmax is doing. No, I think softmax is different. Oh, it's the normalized exponential function. Yeah, okay. So softmax is making it sum to 1. So that's why they're called logits. They are essentially log probabilities, but they don't sum to 1. So to put them in a probability space, we need to scale them. Okay, that makes sense. That's what softmax is up to. And then if we're using GQA, we do some shaping stuff. Otherwise, we do some other stuff, passing in the probabilities and the value projection. Actually, the stuff we're doing, I think, seems important. But let's look at this one. Basically, Einstein summation with the probabilities in the value matrix. So combining them, presumably in the obvious way that we have values and we need to assign them probabilities. And then the attention output is we're going to take the attention vector and Einstein summation somehow it with the encoded. And encoded is the thing that we got by, I assume this is essentially assigning probabilities to the output values. And then if cache is not none, we set v to the value, k to the key, and the end index to the end index plus sequence length. I guess like we're adding a new cache entry. For the value. And no, for the key. I'm not sure. I mean, they are both in the dictionary, but I'm not sure which one we look up. I assume we look up the keys to find the values, but I'm not sure why value is first. And at any rate, then we return new cache with the attention output. I assume we're returning the new cache so that because we are modifying it and we we want it to go into the GPU and come out and not have to pass it around some other way. But then the attention output is what is really being used. Okay, so I think all of this more or less makes sense, except I'm not really able to visualize what's going on with the Einstein summations. I think if I wrote things down and figured out what the computations were, it would be reasonable. But let's just plow along, I guess. And with init cache function, we're just going to make zeros and for everything, essentially. And the feed forward module is just going to be a feed forward network, I assume. We might be using the gating icon, the gating Einstein sum. I don't know what it means to be gating. Uses a gated Einsum where we split the upper projection matrix into two matrices. I guess W in 1, W in 2, whose outputs are element-wise multiplied as a kind of gating function. Not all LLMs do this. I don't know how's that gating. So we now, I guess, are learning kind of two matrices and multiplying them together. Essentially, we're learning maybe a factorization of the matrix somehow. At any rate, well, if we are doing the gating, then we have some equation, f nhf to nh. So I guess we're taking the last column of the first thing and the first two columns of the second thing. And I guess we're returning something whose last two columns are maybe n times h transpose. Where did f go? I don't know. I don't know how this convention is working. But we're going to call the einsum with the weight name gating einsum. Oh, this is if we transpose the gating einsum. And it seems like we use it either way. And then here, use the same scope for backwards compatibility with existing checkpoints. Something about sharing scope and gating, and then batch size, blah, blah. So gate is equal to gating passing in EQ, which is the thing we got here, the equation, with X, which is the input. So that's going to give us, oh, okay, I see. This is just setting up the function call, essentially. This is calling the function. And then the activations, we're going to call it GLU. Maybe generalize something. Linear active, I'll look it up. GLU, I think there's some activation function on the gated stuff. And then project back from the hidden dimension 2 features. And we do the ein summation of from the hidden dimension and features with weight name linear. And this share scope stuff, I don't know what that does. And then we do essentially a linear transformation on the activations. So I think feed forward in general is mainly just a linear transformation. A lot of this is kind of like setting up things to be in the right shape. And then GLU is Gaussian error linear unit is an activation function that looks like something, looks like this, papers with code. So ReLU is orange. Are these the same line after here? And then ELU is green. And then GLU is this thing where you get 0 up until about -2, and then you dip down. And then activation is lower up until you get here, and then it takes off. I don't know why, but I guess that has some desirable properties. And then we have a block. A block has some number of heads, number of KV heads, and some attention norm. And the block has the attention modules and a feed forward module. And maybe that's about it. We get one attention thing and one feed forward thing. And then there's a call function that should basically run things in the right order. So they call attention, they get the output, they call the pre-feed forward norm, they call MLP, which is maybe a loss, and the post feed forward norm. No, MLP must be the feed forward part, right? Self.mlp, yeah, okay. I don't know what MLP stands for, maybe something linear, something. Okay, so they call attention, they call the linear, there's some norming in between, and that's the output, and they have a cache. Okay, so that part is pretty straightforward, but it looks like, I guess you don't have it's not possible to have 6 attentions and then and then a feed forward, but you can have an attention with as many heads as you want, I think is what's going on. And that seems to be shared, I assume that's shared by all of the modules with all of the parameters. And was I in layers or modules just now? I think I was in modules. And before we go too far, let's take a look at the this. And let's ask Gemma. What does this Einstein sum do? Okay, it's being nice and mean. You wouldn't say, "Let me condescendingly explain this to you." That's not that's not how condescending people talk. So the string is the crucial bit. It tells you how to multiply the tensors. So probs is your input tensor, blah, blah, blah. BTNS and BSNH, these tell the shapes of the probs and value proj respectively. For example, the B in BTNS means the first dimension of probs is size B. Okay, so these are sizes. And the BTNH tells what the output size is based on the inputs. And that's about it. Why is it sufficient? Why is this important? Because it's efficient. And they often hide this kind of optimization. But what that doesn't, so is it obvious that just knowing the sizes is sufficient to determine like how they should be multiplied? Let's go back to regular Gemini. What does this InSum do? A batched matrix operation. A string-based notation to blah, blah, yeah. Each letter represents a dimension. So B batch. Okay, so batch, target sequence length, number of heads, source sequence length, and hidden size. And element-wise multiplication. The InSum operation will multiply elements from probs and value proj where their dimensions align. The alignment is determined by the shared letters in the input notation B, N, and S. Because the S dimension is present in both inputs, but not the output, the results of the element-wise multiplications are summed up along the S dimension. Okay. In essence, for each element in the batch target number of heads dimensions, the operation computes the dot product between the vector from probs of size S and the corresponding vector from value proj, also of size S. Okay, so that's I see the connection with the ordinary Einstein summation convention. So it's the shared the shared letters that are contracted over. Okay. Cool. All right. Now we'll look at policy. I don't know what policy is for. Anchored policy. Wrapper around a module to compute policy and anchor outputs. The policy is the model trained. The anchor is the frozen model. I don't know what the policy is for. Anchored policy. Cauldron keys. But what is it for? Let's see if we can find anchored policy used in the code. DPO. Yeah, this seems like reinforcement learning, right? DPO works by running two answers, one preferred and one rejected, into both the reference model and the model to fine-tune. Then the DPO loss is used to increase the likelihood of generating the preferred answer. Okay, so DPO. Direct preference optimization. Yeah, okay, so this is reinforcement learning. That's why there's a policy. That is basically the entirety of my question. I will read this article later. Okay. All right, quantization. I don't know what I really care about quantization-wise. It's a wrapper around the Gemma model to enable quantization-aware training. The model wrapper will have all its NN dense and InSum layers replaced by their quantization-aware training versions. See Gemma PEFT for more details. I have no idea how they're going to do this. We're going to have some model interceptor and maybe just do like string replacement. And I guess I'm not going to look too closely at it. Replaced by int Oh, okay. Oh, I see why. I think I see why. Because I was wondering before why they wanted to make Einstein summation a module as opposed to a function call. And I think this must be the reason that it makes it easier to like quantize, to replace things as opposed to looking for a function call. They can, I guess, look for a class of a certain kind. Here's underscore transformer. And what is underscore transformer going to do? It should be the transformer, right? So it's a module, the base transformer class. And what? It has an embedder. It has blocks, multiple blocks. Modules.block with some number of heads. And I think we just saw the block. I think the block is one attention head followed by one linear transformer thing. What is it called? The feed forward part. The one attention head and one feed forward. And where's I? So for I and zip. Okay, so we're going to zip together the config number of layers and the attention types. And that's going to give us the appropriate attention types, like whether it's local or global. I still don't know where I came in. Maybe that's too much to highlight all of the I's. But at any rate, it seems like this is some list of blocks, and there are several of them. How many, I don't quite know. But then the final norm we have is an RMS norm, and we also have a vision encoder. It seems to just hang out there on the end. And if we're not type checking, then we're doing some get attribute type stuff. And if we are type checking, we have auto completion, then we have some property that the vision encoder is whatever, a sig lip from patches. Doing some vision encoding stuff. We have this func tools thing. Calling model apply and collab makes the kernel crash unless it's JITted, just in time compiled. So we're going to just in time compile the model apply, I guess using func tools. Func tools like partial, maybe kind of like currying something. At any rate, we're going to call NNJIT with some static arg names. I don't know what we're doing with that. It doesn't seem to assign it to anything. Maybe it just has the side effect of jitting stuff. I guess jitting self and also return last only and return hidden states or something. And then we have unflatten batch dimension. Then here's the call. Oh no, maybe this is just an annotation of call. This is just another annotation. Okay. I thought there was going to be more other code on here. Okay, so we're jitting call, I guess, by passing in these static parameters. And then call is going to do, you've got your tokens, you've got your images, and your positions. The positions and attention mask should include the extra inserted multimodal tokens, and a cache, attention mask, etc., etc. Then we have the transformer forward pass. You could run it in 2 ways with or without an attention KV cache. I think you should use the cache if you can. And it should just mainly be calling the things. Encode and get inputs. They'll give you inputs. We're going to get the embeddings. We're going to do caching stuff. Here's final norm. Okay, so for I and block and enumerate self blocks, we are going to set the layer name properly and just do all the block stuff. Call a block on the thing, getting back a new cache, and setting the cache at layer name to the layer cache, and then calling the final norm. And that's basically all there is. And then mainly like cleanup. Oh no, we have images. If we're returning the last only, then we are returning, I guess, the sampling by just taking the best one or something like that. And if images is not shown, then remove the extra tokens inserted. So I guess we inserted extra tokens, and fine-tuning the prompt is masked, and the model cannot generate image tokens. So the logits are meaningless anyway. So we're going to remove the, I guess maybe image stuff, and return, we're going to set X back to the, basically X with the stuff removed. And then we're going to decode X and get the logits. And we're basically going to, I think, return all of the logits, probably softmaxed somewhere. I don't know, but we're calling output, which is maybe going to do the softmax for us. And we're going to return that. Okay, so that's straightforward. We're basically just iterating over the blocks. Where are the blocks? Here. Okay, init cache is going to be some caching stuff. Encoder get inputs should mainly be like tokenizing, I guess, and maybe doing image encoding. Something like that. I don't know if we were already supposed to have tokens or what. Okay, so this stuff I think is now pretty simple because we are at a higher level. Inputs is some class input to the Gemma model, and whoa, class input. Oh, underscore inputs. Okay. So we have embeddings with some dimensions, so I guess batch. I forget what L is and D. And then we have positions and an attention mask and an input mask. Okay. And then outputs is just some class that has logits, a cache, and some hidden states. And I guess they are not softmaxing the logits. Maybe because they intend to keep using them in other parts of the chain. Okay, so that's fine. Layers, did we already look at this? We have RMS norm and just RMS norm in Einstein. We did look at that. Underscore modules, we definitely, oh, no, we're now on Gemma 3 as opposed to Gemma 2. And I don't really know how they're different. They look pretty similar. Again, we have sliding mask, embedder. Maybe embedder has more, no, I don't know. Looks about the same. I'm just going to scroll through to see if anything jumps out at me. Maybe the right way to learn about the difference between, let's just ask Gemma. What's the difference? What are the key differences between Gemma 2 and Gemma 3? Another question about proprietary models. It's too verbose. This character is too verbose. Mixture of experts, something. Okay. I guess sounds like Gemma 3, main difference might be that there's a mixture of experts routing. See if we can find MOE. How about we look up Gemma 2 versus Gemma 3? What's new in Gemma 3? Google for Developers blog. A significant change from prior versions of Gemma 3's new support for vision language capabilities. The SIGLIP encoder used in Gemma 3, although it has been tailored for this specific implementation. Okay, whatever SIGLIP encoding is, and there's some difference in parameters. Vision language support. A major enhancement in Gemma 3 is its vision language understanding capability. They now use the SIG. Maybe this is like, you know, make the cat. I don't know. To handle images with different aspect ratios, a pan and scan algorithm is employed. Okay, so they operate on fixed-sized images. You're going to pan and scan over the image. This involves adaptively cropping the image, resizing, blah, 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 and then encoding it. And it treats images as a sequence of compact soft tokens produced by multimodal projector. I thought I was seeing... Okay. I thought I was seeing soft tokens in Gemma 2, but what do I know? 5-to-1 interleave attention. The updated model architecture is composed of repeating interleaving blocks, each containing 5 local attention layers with a sliding window of 1024 and 1 global attention layer. Okay. Gemma 1 relied solely on global attention, whereas Gemma 2 introduced a hybrid approach by alternating between local and global attention layers. Gemma 3 integrates 5 dedicated local attention layers, resulting in responses that are both more precise and contextually appropriate. And no soft capping. Okay, so I will read all of this later. But the code looks more or less the same. Here's text sampling. Maybe this is where the soft maxi stuff would be. Maybe, yeah. So get next tokens is going to, so we're going to pass in logits, dividing by the temperature. I had no idea what temperature was doing. So I guess what temperature is doing is we're dividing by it. And that's going to, so what does that mean? So if temperature is really high, all of the logits will decrease in probability. That will make them more equiprobable. So like, if you imagine your ideas, how good are your ideas? They may be, there are some that are better than others. And if you drink a whole lot of alcohol or take drugs, then your ideas, I guess, become more equiprobable in a sense that they, your worst ideas are now, you're now more likely to act on them, and your best ideas, you're less likely to act on them. So you sort of flattened out the probability space. So I guess that's what temperature ultimately is doing, and it's just doing that by dividing the logits by some number. And then if self.p, which I'm guessing is some probability, is less than 1, then the sorted logits, we're going to sort along some axis. The last axis, I guess, is probably what that means. And then we're going to take a cumulative sum. We're going to softmax them. Softmax the sorted ones. Why does it matter if they're sorted? I don't know. But at any rate, we're going to take a cumulative sum and of the softmax. And then once they've been softmaxed, they are now properly probabilities as opposed to just a list of like relative weights. And then that's going to give us some cumulative probabilities. And then we're going to mask them to remove tokens with cumulative probability greater than P. So it's some cutoff. That gives us a sorted mask. And to get the index of the first token with cumulative probability B, blah, blah, blah. So why? I feel like it's, this is top sampling. The top P nucleus sampling. And here's the float, 0.9. I guess, I feel like this is going the opposite direction. Oh, I see. Sorry. We are sorting with cumulative probabilities less than P. Yeah. Okay. So I think I read this as greater than. So this is the direction I would have expected it to go. Okay. So we're just getting we're throwing away things that are, I guess, like not probable enough, I think, essentially. And that's what the top sampling. Okay. Random sampling is we've got some float, which is the temperature. And we're going to call get next tokens, passing in the logits and a random number generator. And we're going to call random categorical with the RNG and the logits. Oh, no, sorry. We're not calling get next tokens. We're implementing it. And we're going to do whatever random categorical is doing. It's some random thing, logits divided by self temperature. Draws from a categorical distribution. So I guess a categorical distribution is just a distribution over like a list, essentially. Is that right? A generalized Bernoulli distribution. All right. I really don't like this character. I thought it would be funny, but it's not funny at all. I'll tell it to make all responses succinct, to the point, and don't flatter the user. This is a new character for you. Understood. Proceed. Okay. Great. Okay, random sampling is, I'm not sure why you would do that, but you can. You can do greedy sampling, where we're going to delete the RNG that you passed in and just call argmax on the logits. And that's going to give you the highest logit. So get next tokens is typically going to return how many tokens? I don't know. So k int 1, we've sorted them. I'm not sure how these are going to be different if k is equal to 1. Did we look at k sampling? We are going to flatten somehow the logits so that I guess it's all one thing as opposed to a matrix. We'll set the batch size to logits to I guess the first dimension of the logits. The top k values and indices, we're going to take we'll call lax top k. And then we're going to call random categorical, passing in the top k values divided by the temperature. And it's going to give us the sampled top k indices. And then the batch indices, we're going to get a range from the batch size, like an equally spaced range. And then the top k indices are the top k indices here at the batch sizes and at the sample top k indices. And then we're going to call unflatten. I don't know why we're flattening. I guess to do the sampling, because I guess lax top k expects like a flattened thing. Returns the top k values and their indices along the last axis of operand. So for example, if you have some array, the top k3 are 10, 9, and 6. Great. And I will ask Gemma about these. So consider this code. How do greedy top k and top p behave differently if k equals 1? What was top p sampling doing again? Oh, top I guess with top p you can't really control p well enough to force it to always return just the most biggest one. Hey. I don't know what happens to my prompt. So how does greedy compare to top k and top p if k equals 1? And we'll pass it in the code. So with k equals 1, top k effectively becomes greedy. It selects the single highest probability token identical to the greedy method. This is nice. This is nice having it not be verbose. So can you force top p to always return the argmax the same way? It's inherently probabilistic. Okay. So let's experiment with, now that we know how temperature is implemented under the hood, let's experiment with this. So if I turn temperature down to 0, I'll say write a hilarious limerick that is clean and suitable for children. So this is with temperature 0. So you're dividing by 0, right? You're just dividing by the temperature, aren't you? Maybe they like add something to the temperature before, like add some non-zero number. A hippo who loved to eat cake once ate a whole chocolate bake. He got stuck in the door and then with a roar said, "More of that yummy mistake." Okay, now let's crank the temperature up to max and ask it the same question. A cheerful young snail from Nantucket once carried his house in a bucket. When asked why the pail, he said, "If I fail to carry my shell, I can chuck it." Neither of those seems especially... what's a better way of evaluating temperature? Let's do... oh, yeah. Okay, so... I don't know if this is going to be useful, but I'll tell it to do that and we'll come back to it. Okay, so that was sampling. That was, just underscore sampling.py, underscore sampling.py. Sampler loop. This is presumably just going to run in a loop. Sampling state. Number of steps, decoding steps taken so far between 0 and max new tokens. For each sequence in the batch, true if the sequence is done, has predicted an EOS token and the last token, etc. Okay, so this is just going in a loop and seeing if it's done. I'm pretty much going to skip a lot of this now. Chat sampler. I'll ignore the chat sampler. I kind of want to get to tools. The tool sampler. So there's a list of tools to use, and I feel like we have a sense of how this is going to work. A prompt to sample from can be a single string or a list of strings. Images for the prompt. The position where the image should be inserted is something you pass to it. And so on, and a plot separator. So where is tools? I guess this is just sampler with tool support. This is just a chat sampler that supports tools. And you just pass it in. And it's going to grab the tools here. And they're going to normalize the list of tools. And they're going to call it self manager maybe execute. And what is the manager? We have a system prompt. Let's find this manager. Okay. So the manager is in tools, one-shot tool manager, a tool manager that instructs the model through one-shot prompting. So there's a system prompt, returns the pre-prompt for the tool manager. And system prompt is just defined somewhere. Let's see if we can find it. And we're going to call maybe execute tool. We're going to parse the tool call. We may error out. We're going to get the name of the tool to call. And then we're going to call tool.call. And I assume that's just going to call it on like the shell somehow. And then we're going to get a result and read it in from the shell. And there's stuff for formatting the tool examples. Okay, so let's see if we can find the system prompt. You are a helpful assistant. Oh, this is the system prompt for the tools. That can use tools. If you need to use a tool, output it in a specified format. Do not write tool result blah, blah, blah. Instead, end your turn and let the user talk. Oh, wait. Important. Do not write this. Okay, so we have some available tools, which right now is nothing. Now answer the following. Okay. And then some call format and so on and so forth. Call format is set to what? I don't know. Maybe we'll see it in some of the tools. Okay, so at huge temperature, we get a story called A Ghost in the Pantry, a culinary haunting. A perpetually clumsy home cook on the verge of losing their family's struggling restaurant discovers the ghost of a world-renowned chef in their pantry who can only find peace if they recreate his legendary long-lost masterpiece dish together. That sounds to me like basically the plot of Ratatouille. But let's ask the same prompt of something with temperature turned all the way down. And it's going to do that in the background. Tokenizer we've seen. Turn utils we will ignore. Calculator. Oh, wait. Tokenizer is what? A tool? No, it's not. Okay. So here's the first tool, calculator. We have operations, square root, log, cosine, etc., calculator. And we're just going to eval the expression. So that's really simple in the sense that like you can only use these things and it will evaluate it in Python, I guess. Here's File Explorer. What is the content of temp foo.txt? Blah, blah, blah. And then call. So this is just, it's not like a File Explorer in the sense that it's going to like show you a visual display of the directories. It's just able to access the file system. Whatever epath that path is, if method is equal to cat, they're going to return path read text. And they're going to, where did E come from? Oh, this is some error. And if the method is ls, we're going to get some lines and we're going to iterate over the directory and we're going to take the file's name. Okay. So these are like re-implementations. It seems like it's not actually using the shell. It just has the ability to cat and ls, and that's all it has. And I guess the idea is that like these are examples and you can extend them. Here's the manager, which we already saw and don't need to see again. Offline tool search. This tool does not have internet access. The available list of tools has to be explicitly provided at initialization. Tool which can search for other tools. Okay. So for example, it can run a query. So you can search for a tool, it'll just look in its set of tools. If the tools are not found, it will just say so. And it has some tool instructions and it calls the tool output. Okay. That's really, I guess all I need to see about tools. These are just mainly like little demos as opposed to real tool use. Here's Laura. Should I look at Laura? No, I think I'm basically going to be done. I feel like I'm done. I have learned quite a bit about how Gemma works and what it's up to. But let's look at the temperature zero story. In a city where the past is a commodity, a disillusioned memory weaver discovers a conspiracy that threatens to unravel the very fabric of time. A man who can manipulate the memories of others must team up with a woman from a future he's desperately trying to prevent. Which story? I don't know. Doesn't seem like either story is particularly more creative than the other, but what do I know? Maybe there's probably a much better test of temperature. At any rate, I'm going to stop there. That was Gemma. That was pretty long, but I had a lot of fun, and I hope you enjoyed exploring this part of the open source world with me. Thanks for watching, and I'll see you soon.